The definition of curl, and intuitively what it means, is a little bit more involved than divergence in vector calculus. So if the curl of something, it's kind of how fast and what direction it's rotating. So in this example here, we have, this is going to be the x, y plane. So I have my x, my y, and then z is pointing out of the board to keep it right-handed. Then I've got a point x, y, and let's say there's some vector field defined over the plane. If it kind of looks like the vectors are rotating around this point x, y in the anti-clockwise direction, so like that, then it's going to have a positive curl component. If it's rotating in the clockwise direction, it's going to have a negative curl component. That's going to follow the right-hand rule, I'll show in just a moment. And then sometimes there's zero rotation, so it ends up with 0 for the curl. All right, it's just kind of a couple examples here. So they can be really misleading. You always have to calculate the curl, but it looks like in this one, you have an anti-clockwise rotation, and the arrows aren't terribly big. So anti-clockwise, then it's rotating around this vector here, pointing out of the board, the z direction. And so the way that the right-hand rule works, I take my fingertips, I'm going to rotate them in the direction that it's curling. Then my thumb points in the direction of the vector. All right, so that's how it works. But if I were to come over here, and I'm going to change here, so the length of the vector also determines how much it's rotating. If I come over here, this was anti-clockwise, this is clockwise. So I've got to flip this, but when I flip it, I kind of have to flip the vector too. And then I have this longer vector here because the arrows look like they're going a lot faster, a lot longer. And then following the right-hand rule for this, right, let's see if I can do this, to curl it in this direction. Right, if I follow that way, my thumb points into the board, so the vector that is rotating around is this longer vector because the arrows are longer going into the board. All right, so then in 3D, right, so 2D, there's really only one axis you can rotate around, right? So you either rotate around the z-axis or you're not rotating at all. But in 3D, it's a little different. You can rotate around, there's a whole bunch of axes you can rotate around in 3D. And so what kind of ends up happening, kind of imagine you have a ball, right? Let's say I took the ball and I rotated it, in this direction, like throwing it up in the air so it's rotating. And then while it's in the air, I'm also able to somehow like spin it. And so I spun it a little bit in this direction, I spun it a little bit in this direction, but then that's going to be equivalent. So to point, I rotated it just in one direction by a certain amount, and those vectors kind of combine together, right? So if I do them, this way and this way versus I did it this way, kind of tilted, I can get the same rotation out of the ball. So that's the idea in 3D. We'll do some intuitive derivation of how the curl is defined and where it comes from. So first off, let's get the definition. So it makes a little more sense to start with 3D. So you have the curl of a vector field F. People don't usually write it that way. It's usually written as the upside down triangle, nabla. It's a Greek harp, it's supposed to look like, time cross product to the vector field F. Well, it's got a pretty complicated formula. It's hard to memorize, but there's a nice trick to remembering it in 3D. So you can write it as a determinant of a matrix. So it can be the I vector on top here, the J vector, the K vector. This thing is supposed to be, right, so you're kind of doing partial x, comma partial y, comma partial z, cross product with f. And f in 3D is going to be p of x, y, z, comma q of x, y, z, and r of x, y, z. Close that. So if you cross product two vectors, shorthand to do it is this way, where you write the matrix and you compute the determinant, or just the, remembering the diagonal thing. So partial y, partial z. Right, so that's the upside down triangle. And then the f is p, q, and r. So if we take the determinant of that, where you end up doing these lines. So the first one, I'm getting start with the I component. So I have I times partial y times r. So I get partial r, partial y. And then the other diagonal, right, you do minus, so it's I times partial z, partial q, so minus partial q, partial z. And if I work on the j component, I get j times partial z times p, so partial p, partial z, minus the other direction, other diagonal, j times partial x times r, so partial r, partial x. Then the k component, I get k times partial x times q, so partial q, partial x, minus the other direction, k times partial y times p. So partial p, partial y. Okay. So that's the definition of the curl here in 3D. And that's kind of where it comes from. This is why the notation is used. It's kind of a shortcut. But if you're in 2D, right, so I said if I rotate this in like the xy plane, and then I rotate it in the xz plane, then I can kind of combine those into kind of one direction of rotation instead of doing two separately. You end up with a vector, it points in some direction, and I can, let's see. Okay, I think I did that right. So right, if I rotate along that this arrow circle I drew, it looks like it's going in that vector direction. Okay, so that's the definition in 3D. In 2D, you can only rotate around one axis though, and so sometimes the curl in 2D is written as, okay, where f is of x comma y, it's just equal to p of x comma y, comma q of x comma y. Sometimes it's just written as the z component of this 3D one, because you can only rotate around the z-axis if your arrows are confined onto the xy plane. So sometimes it's just written as partial q, partial x minus partial p, partial y. But then sometimes people will write it as 0, 0, partial q, partial x minus partial p, partial y. Because there's just nothing rotating in the other, you can't rotate in the yz direction, you can't rotate in the xz direction, you can only rotate in the xy plane. So that's the idea, but oh my god, where does this formula come from? Why does it make any sense? Let's go ahead and do an intuitive explanation, and similar to the divergence, but it's a little more involved. For an intuitive derivation of the curl in 2D, so we'll start with a vector field f of x comma y equals vector. We want to find the rotation in the anti-clockwise direction at a point xy in the xy plane. And we're going to do that by figuring out how much flow there is kind of along the boundary of this box. We're going to use that flow to say that's the amount of rotation going around the point xy. Then we're going to shrink down that box until it essentially is a point. All right, so first thing first, let's say, right, we got the sides of this box, so I need to know how long those are. And again, those are going to be delta x and delta y length. All right, the next is I have to figure out how much flow there is from a vector that's on the sides of the box. So let's say my vector field looks something like this. And, all right, got a little crowded there. All right, but right, I have two components of the vector. I have p and q. So for instance, on this side, the part that's flowing perpendicular to the box at side doesn't contribute to flow going around it, but the part that is flowing in the direction will. So the other thing I need is I need to define which way is positive flow. So right, this is positive flow is considered anti-clockwise, so I'm going to need some unit vectors that point in the direction of positive flow on each side. So here I'll have one like that, and I'm going to have to draw them. Here, can I squeeze it in? Okay. So it's supposed to be pretty much overlaid right underneath the side of the box. And same thing here. And here. All right, and here. All right, those are all going in the anti-clockwise direction. All right, so then, it's a A lot of writing, but now we just start adding up all the flows along each side. So let's start with the right side. All right, so that's going to be, this is the vector. And I do have to write here, so I'm going to write it just once, but this is the point x, y, and I move over to here. I'm still at my height y, but x has increased by delta x over 2, right? I'm moving half the box over. The entire bottom of the box is delta x. This is delta x over 2. And then it's at height y. And I'm not going to try and squeeze in all the other f's, but they're all going to be plus or minus delta x or delta y over 2. All right, so the right flow specifically, I have my flow unit vector, which is pointing straight up. So it's going to have components 0, 1, dot product to get the amount of f flowing along that side in that direction. And then write f is x plus delta x over 2. Comma y. And then the last thing, I want to have the total flow on this side, right? Because there's other vector arrows for f all along this side. So I'm going to approximate the entire flow along one side by multiplying by the length of that side. So I'm going to multiply by delta y. Okay. Then if we simplify that, all right, well 0, 1 dot f, well I get 0 times p, 1 times q. So it ends up just being q. Yeah, I can't squeeze it in, so q of x plus delta x over 2, comma y, times delta y. So that's the right flow. And we have the left flow. Pretty similar. The unit vector for flow has changed though. It's now pointing down. So it's going to be 0, comma negative 1, dot product f. Same height y, but I've moved delta x over 2 to the left, so that's going to be a minus. So x minus delta x over 2, comma y. Then again, I want to multiply by the entire side to get the total flow on that side. All right, simplify that. We end up with 0 times p, negative 1 times q, so it ends up being negative q times x minus delta x over 2, comma y, times delta y. All right, then we've got the top flow. Why not? Sure. Okay, and that one, we've got our flow unit vector in the anti-clockwise direction going to the left, so that's going to be negative 1, comma 0. Dot, okay, so this f, we're at the same x value, but we moved up by half the height of the box, so that's plus delta y over 2. X comma y plus delta y over 2. And then I do want to multiply by the side length of the box, which is delta x. All right, and then simplifying that, I have negative 1 times p, 0 times q, so it ends up being negative p times x, of x, y plus delta y over 2 times delta x. And then the bottom flow, the last one, okay, that one, here we go. So we have our unit vector is pointing to the right, so it's 1, comma 0. Dot f. This one is at the same x value, but the height has gone down by delta y over 2, so now it's minus delta y over 2. So x comma y minus delta y over 2 times the side length, which is delta x. So the total flow. Simplify that, 1 times p from the dot product, 0 times q. So we get p of x comma y minus delta y over 2. There we go, delta x. Okay, so now we have the flow in the anti-clockwise direction going along each side. And kind of similar to divergence, we're going to we're going to find the flow as the box shrinks. But right, if the box does shrink, meaning delta x and delta y keep getting smaller and smaller, all the flows go to 0 because they're all multiplied by the side lengths. So right, instead we're going to actually take, okay, what's the total flow around the box divided by the area of the box? So we're going to have the total flow. Yeah, I can fit here. Over the area of the box, which is delta x, delta y. Okay, if we do that, all right, let's start with I think it's the right and the left. Yeah. All right, so I add this to this, so I get q plus delta x over 2y minus q delta x over 2y. That's both multiplied by y. So let me go in here. X plus delta x over 2 comma y minus q of x minus delta x over 2 comma y. Okay, but those were both multiplied by delta y. Then I'm dividing the whole thing by delta x delta y. So this delta y and these delta y's cancel out. And we end up with just this fraction over delta x. Right, but then that's only half of it, right? I've only done the right and the left flow. I also have to add the top and the bottom flow to get the total flow anti-clockwise around the box. So I have a plus. Now this one, I'm going to make this a minus, and the reason for that is I'm going to have this fraction. Okay, so if I have the top flow plus the bottom flow, I get negative p of y plus delta y over 2, but on this bit, I have positive p of y minus delta y over 2. These do end up being partial derivative definitions. So I want to make it look like that, so I'm going to take a minus out of the entire fraction, and then I'm going to put kind of this minus, let's go there, and I'm going to add a minus to this one to get a minus on that. Right, so I'll write it out and do it one more time there. So what is this here? P, let me move the minus down there. P of x comma y plus delta y over 2 minus p of x comma y minus delta y over 2. Okay. So right, that kind of makes sense. I have minus p of x plus delta y, x comma y plus delta y over 2. There's my minus p of x, y plus delta y over 2. Then I have minus, so that's a plus p of x comma y plus minus delta y over 2. So that's how I get my minus plus. But I wanted this to look like a partial derivative definition. So I pulled the minus out. All right, so then same thing with q when I divide it by delta x, delta y. Right, these are both multiplying delta x. Then I divide everything by delta x, delta y. So on the bottom of the fraction, I just end up with delta y. All right. So now these look like the partial derivative definitions, similar to the divergence, right? This has a difference in the coordinates between this x and this first input of delta x. Right, you normally write it as x plus delta x and then just x over here, but it ends up being an equivalent definition of the partial derivatives. So what we're going to do is we're going to define the rotation about this point, the curl, as the limit as delta x delta y goes to 0. So that's all the space I have, so here we go. So the curl, which I'm going to write like this, of f at x comma y, it's the limit as delta x and delta y go to 0 of this thing, so the total flow, over delta x, delta y. But if I take those limits, then I take the limit of this one. There is no delta y in here anymore, so I can just delta x. That's the partial derivative of q with respect to x. And this one is the partial derivative of p with respect to y. So that is how you get from rotation around a box, rotation around a point, and how it relates to the partial derivatives in 2D. 3D actually ends up being very similar. You end up doing the same thing 3 times, and we'll do that next. An intuitive derivation of the curl in 3D is actually really similar to the curl in 2D. You pretty much do the same thing 3 times with 3 different squares. All right, so in this one, I've moved my axes a little bit. So Z used to be pointing out of the board, but now I did red, green, blue. So red is X, green is Y, and blue is Z. All right, we have a vector field now that's 3-dimensional. So in addition to P and Q, there's R. And then I've got some rotation matrices. Oh, sorry. I've got these rotation boxes that I'm going to quantify how much it's rotating. And the dimensions here are going to be delta x, delta y, delta z. It's going to depend which box we're working with, which square, to use either delta x or delta y or delta z. So now we're going to do just one of them. We're going to find the rotation around the x-axis. So let me disassemble out of there. All right. Okay, so we have a square, and its center is somewhere, it's right there, and we've got coordinates x, y, z. We want to find the flow around the x-axis, so we need, anti-clockwise direction again is positive flow, following the right-hand rule. All right, let's see. If I rotate my fingers around in the direction anti-clockwise, my thumb points out of the board. That's the positive x-axis. All right. So now, and keep in mind, this is x, y, z. So the plane isn't x equals 0. We're putting the plane of the board wherever x is. So the box might actually be a little bit further away or something like that, or into the board, but it is in this some x equals some number plane. Okay, so now we pretty much do the same thing we did for the 2D case. So we want to get anti-clockwise flow, so we're going to have some vectors. Okay, that's really ugly. Going around the outside, they're normal vectors for the flow. Okay, I'm just going to draw them a little further away. All right, and then we're going to have the F vector, and I can't draw a 3-dimensional vector on the board, but if it did something like that, then if I project it onto this plane, it's going to look something like that. So we have some vectors again. This is F, and just do that over and over again. Ran out of room. All right. So there's some F vectors, and really the P here doesn't matter. That's the part coming out of the board, because that's not going to go for the rotation. It's only going to be the Q and R components, then only on each side it's going to be either Q or R. All right, so let's go ahead and do this. So we've got the right and the left and the top and the bottom. So we've got the right flow. Okay. All right, so this unit vector pointing in the anti-clockwise flow for this side, it's got 3 components now, so it's pointing up in the z direction, so then the x and y components are going to be 0. So it's 0, 0, 1. And we're going to dot that with the f vector here, and so it's at the same height, but we've moved over in the y direction by delta y over 2. So we got f of x, y plus delta y over 2, z. We also want to multiply that by the side length here. So that side length, if this is the delta y, this is the y-axis, this is the z-axis, this side length is actually delta z. Okay, so that's the right flow, then we have the left flow. Oh, sorry, I didn't simplify it. So if we actually compute this, I have 0, 0, 1, dot product f. Well, that's 0 times p plus 0 times q plus 1 times r. So we get r of x, y plus delta y over 2, z times delta z. Okay, now the left flow. Okay, so that one has this unit vector for anti-clockwise flow pointing down, and down in this case is the negative z direction, and then there's no y component, there's no x component. So that one is 0, 0, negative 1, dot product f of... All right, so our point x, y, z, we move over in the y direction. The bottom length is delta y, so that's y minus delta y over 2. Oh, sorry, x, comma, y minus delta y over 2. And then again, multiply by the length of this side. This is the z direction. This is going to be delta z. Okay. Then simplify it. 0 times p plus 0 times q plus negative 1 times r. So it's negative r times x, comma y, of y minus delta y over 2, comma z, then delta z. All right, so now the top flow and the bottom flow. Looking pretty similar to the 2D case. But top flow, we have unit vector for flow in this direction, so that's y-axis here, so it's negative 1 for y, then 0 for z, 0 for x. So 0, comma negative 1, comma 0, dot product f of... So here we're at point x, y, z. We went up in the z direction by delta z over 2. So it's going to be x, comma y, comma z plus delta z over 2. Plus delta z over 2. Then multiply by the side length here. This is the y-axis direction, so that's going to be delta y. Okay, and simplify that. We end up with just negative q. So we have negative q of x, comma y, comma z plus delta z over 2 times delta y. Then the bottom flow. All right, so the bottom flow, we have the unit vector for the anticlockwise flow pointing in the positive y direction. So that's going to be 0, comma 1, comma 0, dot product f of... All right, to get from this dot down to the middle of this side, we had to go down in the z direction by delta z over 2. So it's x, comma y, comma z, minus delta z over 2. Right, again, this is the y direction, this is the y side, so that's going to be the delta y length there. All right, then compute that. 0, comma 1, comma 1 dot product just leaves us with q in the middle. So we end up with q of x, comma y, comma z, minus delta z over 2, all times delta y. Okay, then we're going to get the total flow. Yeah. That's okay, good enough. Okay, we're going to take the total flow. We're going to divide by the area of this square, not the volume of the box, but the area of the square. So that's delta y times delta z. Okay, so then I'll start with the right flow and the left flow. So I add the right flow and the left flow together. I get r at y plus delta y over 2 minus r at y minus delta y over 2. So I'll just write those out. So what do we got here? R x, comma y plus delta y over 2, comma z minus r of x, comma y minus delta y over 2, comma z. Okay, but then I have both of those multiplied by delta z. Then I'm dividing everything by delta y, delta z. So this delta z and these delta z's cancel, and I end up with just a fraction with delta y on the bottom. Starting to look like the derivatives again. All right. Then I'm going to have a minus. I want to flip the signs of some stuff. So minus, fraction. All right. So I still have the top and the bottom flow to add together. So, all right, this is going to be, if I take a negative out first to make it a little nicer looking, I'll have my negative negative, so positive q, x, comma y, comma z plus delta z over 2. So q, x, comma y, comma z plus delta z over 2. then minus, because I took a minus out, so this minus canceled, this becomes minus, so minus q, I have z minus delta z. X comma y, comma minus delta z over 2. Okay. And those are both multiplied by delta y, divided, but I was dividing everything by delta y times delta z, so I end up with delta z on the bottom. Okay. They look like partial derivatives again. So now out of here, if I take the curl, I have to, all right, here we go. Okay, rotation around z-axis. Sorry, rotation around x-axis. It's going to equal the limit as delta x and actually all of them, delta x comma delta y comma delta z. No, it's not really in this one, or delta x isn't, goes to 0. The total flow. I have to change that name a little. So the x-axis total flow around x-axis, hopefully that's readable, over delta y delta z. Well, right, if I do that, I take the limit, I take the limits here, this ends up being partial r, partial y, this ends up being partial q, partial z. So it ends up equaling partial r, partial y, minus partial q, partial z. Okay, but that's only the flow around one direction. Make sure that's still plugged in. All right, but I have flows in other directions, right? I've got 3 of them. So I've got my x-axis flow, I'm going to have a flow around the y-axis, and I'm also going to have flow around the z-axis. I need to combine them all together. So I'm going to have to erase some stuff. Okay. So it's kind of like, right, if you take a ball, I can probably draw a ball. Okay. And you spin it somehow, right? Well, equivalently, if you could, whatever spin you do in whatever axis of rotation you do, I can get the same spin by spinning it along the z-axis direction, spinning it along the x-axis direction, and spinning it along the y-axis direction, right? I can do 3 of them. And so no matter what spin you do, I could do a spin around the x-axis, and then while it's spinning, I can do another spin around the z-axis, and then I can do another spin around the, I forget which axis I'm talking about, y-axis. So what this ends up being, so I've got the rotation around the x-axis, so I have the curl of f, sure, x comma y comma z, equals, it's got rotation around the x-axis, that's going to be the x-axis rotation bit. Partial r, partial y, minus partial q, over partial z. But I also need to know, okay, if I were to look at this thing rotating around the y-axis, how much is it rotating just around the y-axis? That one, I do not remember off the top of my head, so we're going to use that trick, which is curl f is equal to determinant I vector j, what do you think j is again? Vector k, vector, we got partial x, partial y, partial z, we got p, q, and r. Okay, so let's make sure I did the I one, the x-axis direction, right? So that was I times partial y times r. There's my partial r, partial y. And we got minus partial z times q, so partial q, partial z. The y-axis component, we get j, okay, partial x, sorry, wrong way first, j times partial z times p, so partial p
partial z minus j partial partial x times r, so partial r partial x. And the last one, got k times partial x times q. So partial q partial x minus k times partial y times p. Okay, so right, I take this and I rotate it a certain amount in the whatever x direction. This is gonna be okay-ish, all right. Then I rotate it some amount in the y direction, and I rotate it some amount in the z direction. If I combine those all together, and okay. I think I'm getting this, okay. If I combine those all together, then we'll end up with the axis of rotation. For all three of them, as if you had spun it one at a time. All right, so let's try and do that visually. So there's one, there's two. Come on, there's three. Come on, don't do this to me. Gonna have to edit this out. Okay, I got those to fit back together. So right, you rotate it some amount in this direction, and right, if you rotate clockwise or anti-clockwise, you're gonna point different ways. Rotate it some amount in this direction. Oh shoot. Clockwise or anti-clockwise, it'll point different ways. Then rotate it some around in this direction, clockwise or anti-clockwise, it'll point, different directions. But if you add those all together, they're going to get you the axis of rotation as if you did, just one rotation around this purple axis, and then the length of that is going to be how fast it's spinning. All right, so intuitively that's how it works in 3D. That's why you get these three vector components. That's why it's a vector. You need some axis of rotation for it. And then some very clever mathematicians in the past found this nice way to interpret rotations, where the length of the vector is going to be the axis, how fast it's rotating. The direction of the vector is going to be the axis of rotation. And if it's going one way or another, it's following the right-hand rule, so you know which way it's rotating, clockwise or anti-clockwise, around this vector. But that's it. That's the intuitive definition of 3D curl. You can do it again. So we did x-axis in this case, but you can do y-axis, you can do z-axis rotation, and you'll actually get these back out for the y and z-axis rotations.